analytical one. So the alternate ways to improve your accuracy and all, or if you are not meeting somewhere you have to mitigate, then you have to go that. You again, the way you have generated SN curve for a smooth specimen by scaling based on the material properties between the high cycle fatigue range of 10⁻³ and 10⁻⁶. For 10⁻³ it is 90% of ultimate stress, and for 10⁻⁶ it's a 50% ultimate, as long as it's ferrous material. And for aluminum, that is 75 to 80% is 10⁻³, and there is no endurance limit. Fatigue strength at 5 into 10⁸, you should take 40%. That we already seen in the last class. So you can again generate a SN curve. SN curve for the required KT value based on the related material properties. So to start with, you can take KF, but you can calculate KF. This is one way of doing approximation, but we can calculate the KF. In the absence of data, the behavior of nurse parts must be estimated. There are mainly two approaches used. There is one proposed by Haywood. You start from the entire cycle, one cycle to 10⁻⁶, but you know that 10⁻³ there is a demarcation, low cycle fatigue, and also Haywood takes care of that. So here the endurance limit for smooth one, what is it is a 50% of ultimate. So this point we know already for smooth. We are generating, this is also generated thing, but to generate for KT of say 2.5 or 3.5 or to 1.5, either you can use KT, again it will be considered, but anyway you have to calculate KF. If you calculate KF is still lesser, then you divide that point to that much. So if it is some value whatever it comes, your KT is equal to 2.1 or 3, you divide that value to down. So this point is fixed, 10⁻⁶. Now we need to know 10⁻³ to get a SN curve constructed or generated. But unfortunately you see it's not a parallel shift. Here you are divided by KF, but here you are divided by K-F, because that is the behavior of the material. At high stress amplitude, your reduction, the fatigue resistance factor KF is not remain constant, because at high stress you have a more plastic deformation. There is another reasons there. So that means you need to know what is K-F. You whatever stress you are getting at 10⁻³ divide by K-F, not by KF. Then you will go wrong. The other gentleman proposed Collins model. He doesn't bother about the 10⁻³ that demarcation point. Straight you are going from here to here. Okay, obviously we are concerned about 10⁻³. The Haywood model is most appropriate. So what this is all characteristic narrative I already explained to you. You need to know what are the steps up to this point, and Q is required, because if you know Q, KT is known, you can find out KF. Now question is how do you get a K-F? That is what I will be talking down the line. And Collins model, same narrative. You need the S-F at this point. Here an endurance limit you can divide by KF. Okay, this is wrong because it doesn't take care of the slope. Will have a different at 10⁻³, but is considering this one. So Jubilean what has done is based on the Haywood model. You have alternate stress. Again, if please observe is coming SA, not S max. This number of cycles. This is a smooth one. This you generated for ferrous metal is 50% of ultimate strength. This point 10⁻⁶. It is a 90% ultimate. This point is fixed. Now to get this, you have to divide by KF. Whatever say KT equal to 3, correspondingly you find out what is the KF. That down the line we have seen now KF is equal to KT minus 1 plus KT minus 1 to whole multiply Q, right? Then you have to find the Q. The problem is your K-F varies with number of cycles. When there are low cycle thing, it is coming close to 1, but it can go beyond more than 1 at high things. So this is the curve one has to use. This standard curve thing where x-axis given ultimate steel, aluminum, magnesium, of course, if you know the ultimate material properties. And this is y-axis is k dash f minus 1 by k f minus 1 corresponding to 10 to the power 3. That's it, 10 to the power 3. So if it's 100, you will get 0.2. This 0.2 is nothing but k dash of minus 1 by kf minus 1 is equal to 0.2. Kf we have to calculate using that relation. Once you calculate kf, then we'll see an example similar to this. Then you can find out the k dash f. Once you know k dash f, then you can construct the point at 10 to the power 3. Whatever the stress at 10 to the power smooth SN curve at 10 to the 3 divided by that k dash f, we will get the curve. So the procedure is SN curve to, again it is corresponding to R is equal to minus 1. Please remember, because the smooth itself is R is equal to minus 1 generating, this is also R is equal to minus 1. Once you generate, again you have to take care of Goodman's equation, that will follow. And also knockdown factor also will follow. The ultimate tensile state a true fracture stress is required at this point to get Kt equal to 1. Not Kt equal to N is equal to 1. That's why you need the true strength fracture strength. The fatigue strength AC for the smooth specimen of comparable size. Then the material characteristic length sigma is required because that equation is given whether used Peterson or newer. They need either rho or A. That's A or rho. Then elastic stress constant factor Kt and radius, so that you can find out from the Peterson or DFM. The variation of empirical formula containing K dash of this graph is required. Based on that, you can find out K dash of. So the important points to remember are: mean stress has more effect in notched parts than in smooth specimen, that you have seen that. Tensile mean stress can increase the fatigue notch factor Kf. Sometimes we have seen Kf is less than Kt. It's a very highly special case where Kf become Kt. Imagine, that is a very concern. You say tensile mean stress can increase the fatigue notch factor Kf. Till now we are saying Kf is more than 1 but less than Kt most of the time, most of the cases. But in some special cases, some cases where Kf become a Kt, but you are doing Kt based on the theoretical stress considered, but in that particular special condition Kf is more, then there you have a different discrimination of test results and prediction, where Kt might be giving value, but when you test it you will get lesser value, not more value, what we say that, very very rarely. That's why it can be fatal in fatigue loading. Compressive mean stress can significantly reduce and even eliminate the effect of stress concentration and save parts. Mean stresses inherent in the unloaded part due to residual stresses are often much greater than the mean stress caused by the external load. What it says is, I already explained you the basics, a concept about how residual stress get induced due to the application load. Okay, so sometimes then subsequently when I applied the thing, if compressive mean stress is still there, you have to overcome to that, then only it will be effective. That's what it says.